Okay, okay. So let's do another one. So the ones that we've done so far uh, are all called the method of disks. Method of disks. Okay, it's a disk, right? Because you have these things, these things, these circles with the infinitesimal thicknesses. People call them disks, right? Because they look like disks. Okay, so let's just do one more of those, and then we'll switch to something a little bit different. So, say, let S be the solid. Obtained by revolving this area y equals root cosine x from 0 to pi over 2. This area between the x-axis, the y-axis, the x-axis, and this line here. So you get this. You have this area here, and this area around the x-axis. Okay. So you take this area, and then you rotate it, right? You spin it around, and you get some sort of solid. Okay? And the question is, what's the volume of that solid? What's the volume of that solid of revolution? Okay, so these things are called solids of revolution. So work on it for 1 minute. This should be pretty easy. It's basically the same thing we did before, right? Same sort of question. So you do your slices. You take your slices and then say what you get. Okay, send the somebody nearby and say what you get. Okay, anyone want to sync? Should be pretty easy. Jin Xiaojing, how about you? Huh? What happened? Yeah. Mm-hmm. What? Yes, exactly. Yeah. Root or square root, people call this. Okay. Yeah, exactly. Right, that's the answer. So this sort of thing. Right. So the thing is like this: somebody gives you a curve, right? Somebody gives you between A and B, right? Somebody gives you the curve of some function, right? Y equals f of x. Okay, and then they'll say like rotate around some line. Okay, so let's say that here's the line, right? Y equals h. Okay, so let's say rotate that object around that line, right? So you take this solid thing, and then you rotate it around the line, and you get some sort of solid, what's called a solid, right? You get a solid of revolution, right? Solid of revolution. Okay, you get the solid of revolution, right? And then the volume, right, is just going to be the integral from A to B of pi times the area of the slice, right? So the area is just going to be, I'm sorry, pi r squared, but what's the r? The r is just going to be f of x minus h, right? F of x minus h quantity squared dx, right? Here was even simpler. We have this function, right? Y equals f of x, right? The integral from 0 to pi over 2, pi f of x squared dx, right? Because we're rotating about the y-axis. We're rotating around the y-axis, right? So the line is y equals 0, right? Your h is 0. Okay. 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 So this is just a sort of formalization of what we were doing before. Okay. Let's do a slightly harder thing where what you do is you cut out a hole in the middle. So this is called washers. Okay, the method of washers. Okay, so let's just do an example. Okay, so example. Somebody gives you y equals x squared, and also gives you y equals 2x. Okay. And says, rotate that thing about the y-axis. Okay. So rotate that thing about the y-axis. Okay. So you end up with this sort of like you end up with this thing, but a cone has been cut out of it, right? There's a cone that's been pulled out of it. Okay, so you have this solid. First off, you start off with this solid paraboloid guy, and then you drill a cone into it, like this. Okay, and you're wondering what the volume of that thing is, right? What the volume of the thing is. You could just you could figure it out in two pieces, right? You could say, I'm going to figure out the volume of the paraboloid, and then I'm going to figure out the volume of the cone, and I'm going to subtract them, right? That'd be fine. You can also do it in one move, like this. You'd say, well, if I take a slice, right? If I take a slice, then what I have is this sort of thing, right? I have a circle minus a circle, right? I have what's called an annulus, or a washer. Do you know what a washer is? Do you know this term? It's when you have a, you're making something and you have a screw, you have a bolt, right? Right? Or a screw or something, and you put a washer, and maybe you have a screw. That's it. So you have a screw. You have a screw, and you put something here to protect the wood, right? That thing is called a washer. Okay. Right? You're screwing something into the wood. You don't want to screw all the way into the wood, right? So you put the washer between to protect it. I don't know how you say this in Chinese. How do you say this in Chinese? Are you all intellectuals or something? You've never screwed a screw? No. Okay. Okay. Anyway, so in English, such a thing is called a washer. Washer. Okay, so you do the cut, and you've got these washers, right? So you're looking at the washer, right? What's this outer radius? What's this radius? What's this radius, right? If we're cutting at height y, right? We cut at height y, right? Then what's the outer radius? Well, x is going to be what? For the outside guy. Root 1, yeah. So the outside guy has root y radius, right? The inside guy has what? Y root 2 radius. Okay. Okay, so so the area of the washer is, pi root y squared minus y root 2 squared. Right? Pi r squared minus pi r squared. Right? Pi big R squared minus pi little r squared. Okay. So then you just integrate the volume. The volume is going to be, well, this intersects when x is 2, y is 4. Right? So you get the integral from 0 to 4 of pi big R squared minus little r squared dy. Right? You notice that the method of washers is basically just the same thing as the method of disks, right? If we write this as two integrals, if we write this as this integral minus this integral, right? It's just what we said before. You're taking the area of the paraboloid, and then you're subtracting out the area of the cone, right? So you could do it that way, or you could do it this way. In fact, it's the same way. Right? It's not all that different. Okay, so area of washers is basically just the same thing as area of disks. Method of washers is just method of disks applied twice. Any questions? Okay. So let me have you do one. Have you do one. So here it is. Yeah. So from negative pi over 2 to pi over 2, you have, and here is 1 here. Okay. You have this rectangle, and you also have this thing here, which is y equals root cosine x. Okay? And I want you to take the difference and rotate it around the x-axis. Rotate around the x-axis. What's the volume of the solid generated? Okay, so you spin, right, here's the x-axis, right? So you spin this thing around, right? And you get some sort of cylinder, but with something removed from the inside. Okay, so take a minute and maybe take 2 minutes and see if you can just set up the integral. Okay, turn to somebody nearby and work, talk to each other. Okay. Okay. So who would like to talk about it? Anybody? Chen Xiang.
Integral negative pi over 2 to pi over 2 pi times 1 square minus cosine x dy.
Dx. Yeah, that's it. Right, simple. Right, pi r squared, pi 1. Right, this height is 1. Pi 1 squared gives you the cylinder, right? Pi root cosine squared gives you the inside guy. You take the outside guy minus the inside guy, and that's the answer. Okay, easy. Questions? Yes.
Did you get this directly, or is it like a simple form?
I'm sorry.
Did you get this directly, or is this a simplified form?
Directly, right? This is it, right? This is, right, you get, remember you get pi r squared minus r squared. Right? Well, what's the big radius? The big radius, right, at any point x, the big radius, right, so here we have your annulus, right? Here we have your annulus, the big radius is 1, right? Is that correct? Is that part right? The big radius is 1, right? And then what's the small radius? Well, the small radius is root cosine x, right? Root cosine x, right? So you get pi 1 squared minus root cosine x squared.
Also,
Yeah.
can you do it in terms of dy?
Could you do it in terms of dy? You could, but not so simply. Not so simply. We haven't. So we'll talk about how you might do it in terms of dy in a minute. But that would be a little bit more complicated. That's so-called the method of shells, cylindrical shells. Okay, but we haven't talked about it yet. Okay. Okay. So let me do one problem which is not a method of, not a solid of revolution. But so here's the problem. I probably should have done this problem earlier before I started talking about solids of revolution. But here it is. So you start off with a cylinder. Okay, a cylinder of radius 3. Okay. And it's a tall cylinder. Okay. And then what you do with it is you cut it in half. Okay. So here, okay. So you cut it in half and you throw away half of it. So you only keep half. Okay. Cut it in half vertically, right? You keep half of it. Okay. And then from there, you slice it. From there, you slice at a 45-degree angle. Okay, so you cut in here like this. Cut down, and you end up with something that looks like this. Bad drawing. You know, something that look like this. So do you see what I mean? Like you've taken your half cylinder and then you cut from the bottom at a 45-degree angle up, right? And you end up with this wedge. You end up with this cylindrical wedge. Okay. So you slice down. Okay, and so the question is, what's the volume? What's the volume? Okay. So I know the picture is kind of bad, but I hope you see what the object is. Right? You've taken your cylinder, you've cut it in half. Right? You cut it in half, and then from here you cut upwards at a 45 degree angle, right? And you get this little corner piece here. You get this corner piece here. Okay. And the question is, what's the volume of that wedge? So think about it for a minute or two, and see if you can figure out how would you approach it. This is a hard one. Kind of tricky. I know. Maybe it's hard simply because it's hard to draw a picture. So let me say it like this. If we slice through the thing at time x, what you end up with is actually a rectangle. Okay. Wait. That rectangle increases as you go farther on, right? But the width changes also. It gets taller, but the width gets smaller. Okay. So try and figure out what's the area. You need to figure out what the area of that rectangle is. See if you can do it. Okay, talk to each other. Turn to each other and say, the area is blah. Okay, would anyone like to say? Anyone like to say what the area of that rectangle is?